Okay. Well, I really didn't say anything too important to begin with anyway. All right, thank you for reminding me. All right, you guys can hear me still? We've got the recording on. We're going to cover Chapter 5. These are the objectives. You'll need to understand why we need to put devices together in networks, and that there is a logical addressing system that gets employed at the network layer, a hierarchical system that allows communication between networks. And this chapter also introduces you to routes and next hop addresses and packet forwarding. If you remember when we did that little trace route to Google, we went through 11 different hops before we actually got to the Google website. Well, each of those hops is a router, and in between each of those routers are unique different networks. So it was hopping through different networks as it got to the network you was destined to get to. So those are routes. It's routers that know about routes. You're actually going to take a look at some of those routes and next hop addresses in the lab on Thursday. So that's introduced here in Chapter 5 too. So network layer protocols and the Internet protocol are one of the same for our purposes of study. Remember, the data gets started with a request for a web page or an email at the application layer. It moves down, transport layer gets it ready, ensures that it gets delivered, and then the network layer is actually enables the device, your device that's sending out the request, to actually reach the other device. Because it's the Internet protocol layer, the Internet, the IP, the network layer, that has the source address where the request came from, you, and the destination address, the web server, the email server, the FTP server, whatever it is, the other end. And it's the routers in between that have to know that and use that information in the network layer to get the data to its proper destination. So routers use the network layer. It doesn't care about anything else because remember, inside the IP packet is all that other information, the transport layer stuff, the application layer stuff, all that's encapsulated in IP. Again, the two the network layer protocol of choice that is sort of de facto standard is IP version 4. So Internet Protocol version 4, that's the protocol that you're going to be using. That's the protocol of the TCP/IP model. That's the de facto standard in all networks pretty much nowadays. Even in your home networks, you know, you've got an IP address. And if you went into one of those triple plays with Comcast or with, you know, AT&T, where you got phone and video and high-speed internet all together, it's all over one IP address that your home site was given. Yeah?
Well, like now, they have like the dynamic one that you change every time you log in. Does that work out, or is that, can you do that today?
Yeah, actually, the address that you're given by Comcast is delivered through DHCP dynamically, but they always give you the same address. So they have it set up so that server, when you come on, will always give you that address.
Sorry, I was reading over chapter 4, talking about the MAC address, but I was wondering if the MAC address was like static or something like that.
It is, and it's lower. It's actually layer 2.
When we change it with the network, are we actually changing in regards to that network? Or?
You can't change the MAC address. It's a physical address. So you can only change it on your device by pulling out the network interface card and putting in the new card. Yeah, exactly. We'll talk about that tonight, the difference between, yeah, Gypsy?
I thought online and it was going to IP version 6. That's what it was really about.
Yeah, we're we're going to mention IP version 6, but it's not part of this, a deep part of this curriculum right now. But yes, IP version 4, when it was developed and engineered, they thought they would never need any more numbers and addresses than what they developed. They developed over 1 billion addresses. And at the time, the Internet had, only had a handful of hosts. I mean, the original Internet had 2 computers. One over here at Stanford or Lawrence Livermore or someplace, the other one back east. That was it, and then there were a few here and there. It wasn't until, the web in the 90s when things started to get crazy, right? And everybody had a computer at home with an address, and but they had to do some things to stretch it. But they've done a number of things to stretch that number of IP addresses. But and we're lucky here being in the U.S. because this is where the Internet started. It was created by the Department of Defense, right, the military, and our scientists working together and engineers, and we got the lion's share of the IP address space, and the rest of the world got little bits and pieces. China only got a small part, and China has 1.4 billion people, right, and they all want to be online. So they're actually going to IP version 6 more quickly there because they just weren't given very many addresses. IP version 4, but IP version 6 is going to make certain things a lot easier. You won't have to do the subnetting and those kind of activities, the stuff we're going to spend all next week learning. But IP version 4 is not going away anytime too soon. It works. They've done some things to make it work, and it's still going to be around. Okay. All right, so some of the basic characteristics of IP version 4. So we know that the transport layer PDU, either the TCP or UDP, the segment or datagram, is encapsulated in IP address information, right, the IP address header. So every TCP segment, every little piece, gets encapsulated with IP addressing information that has the source address, IP address, so the IP address of your machine that's making the request, and the destination address, the final place, the Google web server or the Eagle server, or FTP, whatever it is, whatever you're going to. Now, IP has to rely on TCP for a number of things because IP is connectionless. So no connection is established before sending data packets. It doesn't, it's a strange kind of delivery. It doesn't know where it's going when it leaves the computer, but it just goes, right? And it doesn't know if it gets there when it gets there. Kind of like the Postal Service, I think, maybe, but not to disparage them at all. But
You can get a tracking number again.
yeah. If you want to get transport, certified mail, stuff like that. Yeah. It's best effort, so it's kind of unreliable. No overhead is used to guarantee packet delivery, so we know from our reading of transport layer that it does all that, right? Transport layer will do all that kind of stuff. And it's media independent, which means it can operate independently of the medium carrying the data. So whether the medium is copper cable, fiber optic cable, wireless, it'll work. IP will work over that. That's not true for layer 2, right, and things like that. So that's another thing we've got to take a look at later on. All right, so it's connectionless. Oh, here's the Postal Service kind of thing. So the sender, who's sending the packet or letter in this case, doesn't know if the receiver's home, right, or present when it gets delivered. Doesn't really know when the letter arrives. It does until it gets maybe a call back, which is not part of the transaction. And it doesn't really know if the receiver can even read the letter. It has to rely on other protocols to be able to make that happen. The receiver, on the other end, doesn't know when the request is going to arrive either. So there's no announcement coming forward first at all. So it's connectionless.
So also, the network layer is doing the actual connection. It goes up to the transport layer to check
Right, because remember it has to go up to the transport layer and get those acknowledgments sent back. Yeah, so as it moves up through the layer, it's got to go back and send an acknowledgment. It does this very rapidly, but it has to do all those steps. And you looked at that, when you did the Wireshark thing last Thursday. Yeah. So, as an unreliable network layer protocol, IP does not guarantee that all the packets will be received. Other protocols manage the process of tracking packets. Some, we learn, require that every packet be delivered, right? Certain things. And others, you can miss a few, and it's okay. So that's a different protocol. So UDP, it's okay if you lose a few packets. TCP, it's not okay, right? You need to make sure and have each of those. So they work together. And it's media independent. IP packets can travel over all kinds of different media, and they do as they leave your house to go to some website somewhere, or here from school. As it leaves here, it's copper cable to our back room. From that back room, it's fiber optic cable up to building 1 where our router is. Building 1 router goes through, actually, fiber optic cable that the phone company has put in for us, and then eventually out to a variety of media, including wireless at some point as well. So the IP header, the information that gets encapsulated onto the segment before it goes out, as it's moving down to its transport layer, then it goes down to the segment layer and gets added information, a header. The IP header is called a network layer encapsulation, and the resulting PDU, the PDU at the network layer for IP is called an IP packet. So packets are commonly used to describe all kinds of transmission, right, and all kinds of data units, but specifically it's about the layer 3 data unit, PDU. So in TCP/IP-based networks, the network layer PDU is the IP packet. So it's got some additional information on there, like all the other protocols. Most importantly, it has that source and destination address, right? Source and destination address that are there. That information, all of this, the bits and bytes that are connected here, get added to this IP header. Remember, it starts with application, gets TCP header information, or UDP. This becomes a segment. It moves down as part of the data and gets an IP header connected to it as well. Oh, I got more people online than here in class. I'm afraid that some night I'll walk in here, there won't be anybody here. That'll be pretty weird. I don't know if I can do that. Okay, remember I showed you this graphic repeatedly. The interesting thing is that all along the way, the IP packet remains intact and the same. As it goes from the sending device to the receiving devices, it makes its way through the internetwork going from router to router. All along the way, the data link header information gets stripped off. New data link information gets added on. We'll learn about this when we look at the data link layer in later chapters, but that's different. And it's different because there's different types of technologies that connect those networks together. Here we have Ethernet. Ethernet is a LAN architecture. But when we leave the building and go out into the internet, we're using other technologies, right? We're using frame relay, we're using T1 lines, we're using ATM, we're using wireless in some cases. Those are different protocols that require different framing technologies. Okay. So our focus is on the network layer. And the most important part of that network layer is the source address and the destination address, IP address, that will never change throughout the whole process. So the network layer provides services to exchange data over the network between identified end devices. So they're identified in that they learn the source address and the destination address. Now, specifically identifying the destination has other things working, right? So when you put in a request to google.com, we learned that DNS has to be involved, right? Because DNS has to find google.com in the database and return the IP address that represents google.com, so that can be placed in the packet. And there are other things on local area networks that we'll also learn about later on that help devices on a local area network learn each other's IP addresses and MAC addresses. So that's another thing that has to work together. So nothing works in isolation. All these layers have connections up above and below. So layer 3 uses 4 basic processes. Addressing, so you got to learn that, an address, a unique address that identifies that host on the network. Encapsulation, where information gets added to the data communication that's going out the PDU that's specific to the IP address, including the addressing. Routing is an important aspect of the network layer. Routing is done by routers, yes. Now, if you're in China, you call them routers, because that's what and in England too, routers, and you do routing. I guess it's either okay. It's like tomato or tomato, I guess. But here we say routers, right? Can anybody confirm that? Routers out overseas? You heard that term? Well, it's true. And then it does de-encapsulation on the other side. It's got to take off that information as it moves and looks at the content inside that packet, the transport layer information. Okay, so addressing. There's got to be a source address and a destination address. And as we look, this laptop source address is 192.168.100.1.99. That's the source IP address. When it's making its way to a web server, it needs a destination address. This is 172.16.3.10. Now these look like they're directly connected together. Will this work? Why not? Yeah, they're different networks. They have to have different addresses. Otherwise they wouldn't be able to connect either. But these are different networks. We'll talk about that later. Now, from the perspective of the source of the destination over here, it's when it responds back, it's the source, right? And the destination is, right, the one that it received from the source, the request. So source address, destination address differ from the perspective of the host. Now what happens in between here is what enables this connection to be done. Remember, this is just like our lab. When we do our labs, we're going through 2 routers, right? We got the central office router and we got the ISP router. When as we make our way to the Eagle server, it's a different network, right? But it works. Okay. Oh, I guess I did include this slide in here. Remember, we request Google, HTTP header for that website. We have the TCP information. We know DNS is there and everything, so we need to get the IP information, source address of this device and of the destination device as well. Data link moves down. The router grabs this packet, strips off the framing, because it has to look inside and look at the destination IP address. Because it has to know, where is this packet destined to go? Well, it takes it off, looks at the IP address, determines whether it can route that packet or not by consulting its routing table, looks at the routing table and says, okay, that packet's going to go here, okay, I got to send it over here. Just like in the post office, when they're sorting the mail, they do it by zip code or something like that, and they throw a letter in that bin, and that one goes in that bin, and that one's going to go in that bin, because they're going to go to different destinations. Same idea. So when it's ready, it knows what it's going to route, it puts a new data link on there, sends it to the next hop router that it's connected to, And the same thing happens there. Receives the packet, strips off the data link, the framing information, opens up, looks at the destination IP address, which hasn't changed, right? It's the same one that was originally found over here, and looks at its routing table, says, oh, I can route that. It's got to go out to this other interface, adds a frame, sends it out, and so on. This happens all along the way until it gets to the Google server in this case, strips that off, looks at the IP address, says, oh yeah, that's for me. Oh, it's TCP, I got to send an acknowledgement that I got it, right? First, to set up a connection. Oh, it's HTTP, that's the application, that must be for my web server, Apache, right? And it can read it, present the file, and then return the web page. Okay. So encapsulation is adding information to the data at each level. So application layer adds a little header, right? The HTTP, the FTP, the Telnet, DNS, whatever it might be, all those applications. Moves down to transport layer, it encapsulates additional information, TCP information, or UDP information, port number, right? Those kinds of things. As it moves down in the data flow to the internet layer, it has to add the IP header, source address, destination address. Then when it gets to the network layer, that's where it's going to get out on your cable, right, the Ethernet cable. It needs to add a header there that actually has the physical addresses that you were talking about earlier, Ryan, the MAC addresses. That gets placed in there.
In the encapsulation.
In the encapsulation, the header of in the network access layer, data link.
So the packet is never really changed. It's just a frame around the packet.
Exactly, exactly. The packet remains the same from start to finish. And is looked at all along the way at every hop. Strip it off, look at it, determine what that's what routers do. They look at the network that this is destined to go to. They look at their routing table, which we'll get a chance to look at Thursday, and they send that packet along the way. And it works, right?
Routers,
oh yeah, they have, a router is a computer. It has a motherboard, it has RAM, they use flash. So they have flash, like a static flash memory.
But if you turn it off,
well, it has a battery, just like all your motherboards, right, that keeps certain information charged. Yeah, if you turn it off, it's not going to route, but it will retain its configuration. Just like a computer retains its date and time and everything, even though you shut it off, because it has a little battery, a lithium battery, right?
Are they all programmable, or they pretty much come with everything that people have?
You have to program the router to get it to route the way you want it to. That's what you're going to learn in the next class. The second 8 weeks is all about programming routers. And actually we'll touch upon that in this class, the last chapter. Start configuring the routers to do. Remember, I've got to show you this little video at some point of the warriors of the net. You'll find out who the hero of the network is, and it's definitely Mr. Router, or Mrs. Router, or Ms. Router, or whatever you want to call that device. Yeah. All right, so decapsulation or de-encapsulation, there's a couple different ways to say it, is what's happening at the other end when it arrives at the destination that it's going to. It arrives there at this machine. It has to go up through the layers. It has to de-encapsulate. It has to strip off the network layer. It looks at the IP address. It has to strip off the IP header and look at the TCP segment information. Say, well, what port is this for? What application do I have to give this to? Right? It has to do that all the way. That's decapsulation. That's done at each layer on the other end. So layer 3 decapsulation, when the packet arrives at the destination host and is processed at layer 3, the host examines the destination address to verify that the packet was addressed to this device. And it'll know because it's been configured, right, with an IP address and subnet mask, right, and gateway. If the address is correct, the packet is decapsulated by the network layer. The layer 4 PDU, the segment at the other end, is contained in the packet, is passed up to the appropriate service at the transport layer. So the other thing that the network layer is responsible for is routing. So routers examine layer 3 destination IP addresses to forward packets. They search their routing table, so they're programmed, and in their RAM, right, in their random access memory, they have a routing table with all the information. If it's this network, send it out of this interface. If it's this network, send it out of this interface. And routers have multiple interfaces connecting to different networks. See, this one right here has 3 connections, right? In fact, they all have 3. And maybe this is another one, 4, right? And here's another one. So they have a lot of different interfaces. Port, yeah, ports. Now your PC typically has one interface, right? The PCs out in the lab have one network interface. My laptop actually has 2, right? I've got an Ethernet and I've got a wireless. So it has 2 different interfaces. So it actually can do routing. I can take information, I can plug in and I can have people connect to me wirelessly and get out through my machine. I can make it a router and make it give everybody else internet access. Right? I could share my internet connection as a router would. Yeah, it's like tethering that to that device. Similar, yeah. Okay. So the router searches the routing tables. Every router's routing table is a little bit different. We're going to learn about that because this router knows about all these routers, right? But it may not know about other routers further down the line. So they have to work together as they make this packet get delivered. So they send the packet on to the next hop router. So here in our network, if our PC doesn't know this address, it's not part of its network, where does it send it? When it gets a packet that's for some other network, where does it send it? The gateway. The gateway, that's your router. When it gets to the gateway needs to know what to do with it, right? So it's going to Google. Now I can tell you our gateway on this lab doesn't know where the Google web server is. But it does know what to do with an IP address that's not in its routing table. It sends it to the next hop router because our router for this network is connected to another router, which is connected to another router. And they work together routing this information. And we'll see how that all works very soon. But let's move on here. Any questions from those of you that are online? I haven't really been paying attention to you guys much. Thank you for telling me about the recording, though. Yeah, you know, I can't see that recording button from my end, but I can see it over here on your end. So that's another limit here. All right. So the IP header has a lot of information. You're not going to be responsible for much of it, really, all of it, rather, just some of the things. Most importantly are the source address and destination address. And each of those values is a 32-bit binary value. So it's 32 bits, right? That's 4 bytes. Remember, each byte is 8 bits. Remember, we learned bits and bytes a long time ago. It's even with the old PC 8088, we had bits and bytes there, too. Okay. All right, so the IP destination address is a 32-bit binary value that represents the packet destination, and the source address is another 32-bit binary value that represents the packet source network layer host address. Now, when you're typing in your IP addresses, you're doing 192.168.1.10 or something, right? So you have these 4 numbers. Well, we type those numbers in decimal values because that's what we understand really well. But computers don't understand decimal numbers very well. It has to convert everything to binary numbers, the zeros and ones, right? So we have to convert that. Why do we do 10? Why do we pick 10? Why do human beings have to do 10 base numbers? Yeah, this is the early calculator right here, the first computer for our 10 fingers, right? So that made it easy to do powers of 10, because that's what we have. I mean, some people have an 11th digit or something, but that's just that's not normal, right? That's just so yeah, it's 10. Okay, so computers though they don't do that 10 very well. They do binary much more easily. Okay, so there is going to be some requirement for you to be able to convert those addresses, those 10 base numbers, the 192, the 168, to binary values. We're going to take a look and do some of that, and you'll get pretty good at it. It'll be helpful, but it's not going to be your method of solving addressing and subnetting and those kind of things that we're going to talk about next week. We're going to have to think of some quicker way to be able to solve those kind of problems. So I'm going to show you some shortcuts that will help you do well on the exam, where you have to answer questions quickly because you only have 90 minutes to answer 50 questions. Yeah.
So how does that look like? Is that like the top part, like the first four, left, or
Oh, it would look as a whole string of zeros and ones.
that looks like there'd be more than 32 bits.
Well, it's 32 bits just for this, Ryan. Another 32 bits just for this.
Oh, okay.
This is 24 bits, or actually a little bit more.
I was like trying to figure out how that would happen.
Yeah, the type of service is 1 byte, it's 8 bits. The protocol that it is, IP, whatever it might be,
32.
right, it's more than 32. It's just, well, it's 1, 2, 3, 4, 5, 6 times 32 bytes for the header, right? Because each of these is 32 bits. So 192 zeros and ones all in a line that go out on that wire. And a 0 and a 1 is a, you know, a positive or negative charge, right? Those go out, I mean, really rapidly, right? But that has to go out on that one packet. And every packet has 192 bits of header information. And another, you know, more than 192 bits for TCP information. Plus the data, right? The movie you're sending, the music file that you're trying to download, right? That's millions of bytes.
How does it work with the left going to send that first, and then it's just going to start streaming the data?
Streams it out, yeah, exactly. 1 bit at a time. You got it. And then it has to have something to, you know, for checksum to know when it ends, the packet length, those kinds of things. It's all there too. Yeah, nothing's magical about it. It's all kind of has to add up.
Is it a 24 byte header? Is that what the show is? 4 by
1, 2, 3, 4, 5, 6 pieces of information, each one of 32 bits, right? And that's not that critical that we understand that. We're not going to need to analyze that unless you become a, you know, a software electrical engineer that's going to work on these protocols, right? And even then, it's always done in, you know, as you know, one team working on one small piece of the whole process and trying to make it better. So one of the fields that you need to know about is the TTL field, the time to live. So when a packet is first generated, if that request first comes up, a value is entered in the TTL field. Originally, the TTL field was the number of seconds, but you know, then they would just time it. It was like a timer. If it didn't get to its destination over a certain time, it would die, right? So that became more difficult to implement and to use. So now, the time to live is set to a specific value, and then it's decremented by each router. So it starts out at a certain value, and as it routes, each router will take one away from the time to live. So with each route, it has less time to live. So the most common routing mechanism or metric is the one you'll learn about first, is hop counts. So if this packet is going through too many hops, we don't want it to just infinitely go traveling around in the web, right? Being passed router to router. It's got to if it's going to be an infinite loop, we want to stop it because it doesn't have a destination that's known. So it has to have a time to live. We don't want these things out there routing forever. Okay, so there's a value that's in there that indicates the time to live. So if the router decrements the TTL field all the way to 0, it will drop the packet, unless the packet is destined specifically for the router, like a ping or telnet, etc. So here's some common operating system TTL values that are in there for different devices as well. You can see they have different operating systems have different ways of decrementing the values, depending upon how the network is going to go. On an internetwork, the routers do that. And each routing protocol that you learn about in the next class, there are different routing mechanisms to do routing. Some are better than the others. Some have advantages over others. The first one you learn uses count, hop count. It's not always the best because sometimes your hops, like sometimes you might have a network that's just 2 hops away, but it's over dial-up. And 2 hops of dial-up is a lot slower than 3 hops of T1 lines. Right? So the 3 hops of T1 lines is a much faster connection than the 2 hops of dial-up. But some routing protocols just use hops. Doesn't matter what the bandwidth is. So those are some differences in the routing protocols that you'll learn about. So there's a time to live field. So IP packets don't go out there in the network living infinitely. They will be removed after a certain time if they're not delivered. The protocol field enables the network layer to pass the data to the appropriate upper layer protocol. Now, above IP is transport layer, and most of the transport layer is TCP, but there's other protocols too. Remember, we learned about UDP, so there's a value for that as well. And then ICMP is another one that's kind of unique. What is the ICMP? Ping. That's the ping command. It uses ICMP, a different protocol. So ping and traceroute, those network tools use ICMP. Type of service is another thing you should take a look at. It's used to determine the priority of each packet. So this becomes important too. This was something new because in early days there was just email, file transfer. I mean, there weren't a lot of different types of communication going over networks, but as networks expanded and grew and became capable of sending out other types of communications, then you needed to have some kind of field in the IP header to enable high priority traffic like voice over IP video to get through first. I mean, an email, you can wait for that, right? If you wait another 2 minutes for the email, that's okay, right? Sometimes you wait longer than that. Sometimes you don't care if you get that email right away. You don't even want to look at it, right? Things like that. So a type of service can help implement quality of service mechanisms, things like that. So there's some other fields. I have a slide here just to describe each one of those. They're not going to be critical. You're not going to be held accountable for any of these on the test. The version's kind of interesting. These are all going to be IP version 4, the version number, but we've got new IP addressing that's coming into play as well, IP version 6. Okay, so IP enables you to divide your networks. So network designers have to ask, on what basis should the network be divided? All devices on the same network share the same network address. So when you and your partner are out in the lab, you do 172.16, right? That's your network. And then you can choose whatever you want for the other 2 numbers. The 172 and 16 is your network. Here in the college, we've got 10.1 is our student network. 10.2 is our student network. We have 10.1, a different network for our admin, for faculty and staff. It's a different network. So you can divide it between floors, you can divide it between locations, you can divide it between departments. There's all kinds of reasons to divide your network out. If you do that, you have to have a different IP network address. for each of those. So we grouped devices together into networks. So early days, we connected everything with cables. We used switches or hubs between all of those to connect them. In an IP network, all of these devices, servers and computers, have to have the same IP network address. They have to be on the same network. They each also have to have a unique host portion of their network. So the most typical network one at home is your 192.168.1, right? Every device in your home network probably has 192.168.1. And then the fourth number is unique, right? 1 is your router, 100 is one of your hosts, 102 is another one, 103 is another one. Everybody on your home network has to have that fourth value be unique, right, and not shared. So replacing the middle switch with the router creates actually 2 IP subnetworks, hence 2 distinct broadcast domains. All devices are connected, but the local broadcasts are contained. So let me go back up to that previous screen there. I wonder why. Okay, so on this network, you may have seen that a little bit in the lab where you see a lot of traffic on your device with Wireshark. Right, there's a lot of packets that hit there. LANs, local area networks, are very busy places. High speed, lots of traffic, a lot of things going on. Everybody hears everything, but you only, grab and take what's destined for you on a LAN. But you hear everything else, all the other conversations. And it creates a lot of traffic. So you can segment that traffic and reduce traffic by dividing your network into different networks. And that's what routers do, too. So replacing the middle switch with a router creates 2 subnets. That way, any information that's on this network that everybody hears about will only be heard on this portion. It will not go through the gateway to the other side. Anything that's just, from this host to that router or that server or this host to that host will only be heard here, not across the network. If this client wants to get access to this server, it has to traverse the network. The IP address for this network will be different than the one for this one. Okay. So you could also group devices, separate networks for security purposes. So here, right, at our school, we've got a student network. We've got, the admin network, or you might have a research network, and you divide them out. So these 2 networks have different IP network values, not the same. And we group devices into networks using a hierarchical IP addressing scheme. So hosts do not know how to deliver data to devices in remote networks. That's the role of the gateway. So the gateway is the key device. It's the doorway out of your network to someone else's network. The gateway, right? And it is a gate. And the gate is closed unless the packet has a destination address that opens the gate and allows it to go out and out to another network. So the address for this destination is unknown to packets and are passed to the gateway router. The gateway router hopefully can find the network, right? That's what they're programmed to do. So the addressing is hierarchical. That means it has different parts that allow you to separate the networks and find them more easily because they have this hierarchy. So it's kind of like a good metaphor are the Postal Service and zip codes. So different zip codes are part of the different mail networks that are out there, right? So here in the Bay Area is a good case in point. We've got, and this has grown over years. So the 30+ years that I've lived here, more than that now I'm thinking about it, we've added additional zip codes, all right? Same thing with phone numbers and area codes. We've added those too over the years. So I know I live in Pleasanton. We used to always be on the 6.6 network, but now there's 8.8. 4.5, 8.8, and 6.6. They've added because they've added more houses, more addresses, and they needed to divide up the networks. So the letter from Japan has to know which country it's going to, and then when it gets to the country, which zip code in that country, and what address, the street address. There are a lot of people that live on my street, but they have a unique home address, which is sort of that host address. So those houses on the street that's going to a person that lives in that house is like your computer network. You have a unique home address, right, along with a unique network address as well. So IP addressing has two parts, and we'll cover this in a little more detail in the next presentation, right? Remember, it's 32 bits, right? We determined that already. So 4 bytes. You can divide it up into different parts, but part of the network from left to right will be the network portion. And the portion on the right that is decided can be the host portion. So here's 192.168.18. That's the network, right? Those are the first 3 bytes. And the last 8 bits, in this case it's 57, is the host address. So there can be other hosts on this network with the same network address, and they can share that same network. So 57, 58 would be a different host, right? 59 would be another one. 56 would be a different one. 1 would be a different one. As long as these numbers are all the same and part of the network. These two parts, the network and the host address, make up the complete IP version 4 address. Okay, on a bigger network, this is 172.16. That's kind of what we're using out in the lab. Every device has to have a unique address, right? Here's 10.100, 20.77. There's a lot of possibilities with 16 bits of addresses. In fact, later we'll learn that with 16 bits you get a lot of possible combinations, right? It's 2 to the 16th power. 65,000 possible little hosts can all have a unique address on there.
What is that slash?
Yeah, that refers, as you can see on the second bullet there, to the subnet mask, which will be discussed soon here.
Is it regional or also like 192.160 or 1?
It is actually. The 172 and the 192 and the 10 are kind of special addresses that we'll learn about in the next presentation too as well. The /16 is the subnet mask. You know how every time you type in an IP address you have to put in the subnet mask too? That's the 255.255. In the lab we're doing 255.255.00. That's /16. Because 255 is 8 bits, 255 is another 8 bits, that's 16, and then 0 and 0, the last 16 bits are not part of the network. So we'll talk about that in a minute. So the mask is critical. You can't give something an IP address without the subnet mask. You have to have the mask. Okay. So intermediary devices such as a switch may have an IP address on this network that allow the network administrator to telnet to the device for remote management, but typically switches are layer 2 devices. So we'll learn about them in the next couple of weeks here. Host IP addresses are members of a group of addresses called a network address. Where do they come from? Well, the Internet Assigned Numbers Authority, IANA, have the responsibility for allocating network addresses. Company or an individual needing a network address typically goes to their ISP for that. So an ISP, Internet Service Providers, they handle the addresses and they'll allocate them. So from your home network, you have one IP address given to you by your ISP. Now, these addresses here that are in this private network are unique addresses. They're private IP addresses, so there's certain ranges of addresses that are dedicated for the use in the private network. Your 192.168 address that you use at home, I use the same one at home. It's private. But my home is not directly connected to your home, right? It's not on the same network. I can get to your home, but I have to do it through the internet, through my internet service provider, like not directly connected to it. So those networks can be different. Okay, how do we assign them? Well, we know you need the default gateway, so you need an IP address, a subnet mask, and the default gateway. Devices on this network go through the gateway. The gateway has an IP address, 172.16.1.1. That's kind of typical. It knows how to get requests for information and communications outside the network by sending it to the ISP. Right? And the ISP has a connection to the internet. It's the internet service provider. The internet is that web of networks connected together. Right? So a router, which is used to forward packets out of the network, this is the host IP address on the router. The default gateway IP address is typically a host IP address which is on the same network as the host itself. The host only has to be aware of its own network and the default gateway. So if the host has a packet that has a destination address that's not on its network, it has to send it to the gateway, period. That's what the gateway's for. If you're not going to have access to the internet on your LAN, you don't need a gateway. You can just keep everything on your private network. In the 80s, that was just fine. Nobody connected their networks together from remote distances. Well, we could do some, but not too many did that. Okay, so on each of these devices, they each have a unique IP address, 172.16.10.100, 172.16.10.55, 172.16.10. What do they all have in common? 172.16.10. That is all in common. That's the network. The gateway, well, that's not, it's 172.16, including the gateway. 172.16.1 is different. So they all, actually all have the gateway address configured as well. So you do that. You configure those three things in your host: IP address, subnet mask, and the gateway.
Now, can you have more than one gateway?
If you do, you're going to need two different interface cards, right? So you could plug in another NIC, right? There's a slot on your PC. You could do that. But then you're basically like a router, and desktop computers can route. Oh, yeah, it could, sure, but then you would do firewalling kind of stuff between them too. But it's not typical. Typically, end devices on a network have a single gateway. Well, the servers are another thing. Servers like another host. Like the devices here could be servers too. This happens to be a printer and a couple of laptops, but it could be a server here too. That it's the router that has multiple interfaces. Because, yeah. Usually they're on a high-speed line, right, on the network, gigabit or 10 gigabit lines, something like that. But no, all the hosts of the same network will typically have the same default gateway IP address. Okay, how do you confirm your IP address and default gateway? You do from the command line, ipconfig, shows you all those values. Subnet mask is there too. Notice the mask is 255.255.0.0. That tells me that the network value is 172.16, and the host number is 10.100. And the host number of the default gateway is 1.1. But the network value for both of those is 172.16. That's what they have in common. If you do ifconfig on a Linux box, you'll see the same thing. The inet address is here, 172.16, 1.100. I don't see my gateway address here. Broadcast address is there, but no gateway. So anyway, you can see on Linux, if you want to see the default gateway, you have to run a netstat command -rn for the default gateway information. So different operating system, different method of finding those values. Okay, now you can take your network and divide it into sub-networks. This provides for several benefits that we'll talk about later, but we can divide it up. So these are separate networks. But in order to subnet your network, I had to add some additional devices here. What devices did I add here? More routers. Every one of those networks has their own unique router. So if we're going to have networks, separate networks, and we want those networks to be connected to one another, you need routers to do that. And these are different networks. So this is the 172.16.10. It's a /24, which means the first 24 bits, 8 and 8 and 8, are networks. So the subnet mask is 255.255.255.0. Remember, the old mask was 255.255.0.0. In this case, it's the first 24 bits are network. The last 8 bits are hosts, which means I can only have 8 bits per host, which is 2 to the 8th power, 256 possible addresses per host. So you can't have 1,000 hosts on that network. We're only, and most networks are that few number, right? So in this case, we've got 4 different networks: the 172.16.10, the 172.16.20 network, the 30, and the 40s are all unique networks. They all share, all these devices on those networks share the same network address. 172.16.20, 172.16.20, the gateways 172.16.20.1, and so on. Now routers have to know where the next hop address so that they can forward the packet to its destination. Remember, the host only knows the address of the devices in their network. If I don't know the address of the destination device, I send the packet to the gateway by default, so it goes to the gateway. Now the gateway needs to know what to do with that packet. Now this particular gateway knows this network, the 192.168.2, right? Because it's part of that. But it's also connected to this network, the 192.168.3. So this router knows 2 networks, the 2 and the 3. Well, no, actually, no, it doesn't know the 3. It knows whatever this one is, which is not identified here. So let's say this is the 1 network here between these two, because this is a separate network in between these 2 routers as well. Here's the gateway for 192.168.3. So routing a packet, if this packet is destined for a device in the network, no. It is destined for a device 192.168.5.6, a device on another network, way over here. So it's going to forward it to the gateway. The gateway is going to say, do I know that network? If not, I'm going to forward it to the next hop router. And that one will do the same to the next hop router until the destination is found. So how do routers work? Well, they use routing tables where they have different networks that they can send information to. Packet destined for network 10.1.1.0. I want to forward the packet so that it can take the next hop towards the destination. I can use information in my routing table to determine where to forward this message. So in that routing table, it should have some information. If it doesn't know where the 10.1 network is, then it will send it to the next hop router. And the next hop router knows in this particular case. Now remember, in our little example to Google, we were 11 hops away. I mean, those early routers didn't know where Google was. It just knew where to send that packet to the next hop, to some router that didn't know what to do with it. So a local router's routing table has information in it. It has a destination network. This is the local router, the 10.1 and 10.2. It's there. And it says the next hop address is 192.168.1.2 for both of those. So we'll learn that this router learned about these networks by being told by this router what they were. Because these 2 routers are connected to one another. They're neighbors, and they talk to one another. And it's not rumors like some neighbors do, right? It's real information. Okay. So here's a routing table. If you look at it, you can actually log onto the router, show the routing table. It's called the command show IP route. You do it from the command line. You'll actually see the routers there. I'll say this network is destined via this interface out of that fast Ethernet 0. So it's a table of information that actually, it's not magical. It tells the router what to do with those packets. You can actually take a look at the routing table by logging in. You're going to get a chance to do this in the lab on Thursday. You'll log into the router through Telnet, and you'll check the routing table that's in there. You can also do a routing table on your own PC. Every PC that's connected to a network has a routing table. So we'll take a look at that too in the lab. All right, so route entry exists determines what the router will do with this. So remember, a router receives a frame of information. It decapsulates the frame, takes it off. It looks at the destination IP address, so it extracts that. The router checks the routing table if there's a match. Here's a destination network. Is that in my routing table? In this case, it is. Network 10.1.2.0 is found in the routing table. The router re-encapsulates the packet with a new frame and sends it to the next router. Now, static routing is done when you actually write the routing information. The network administrator types those in to tell it what to do. So configures each route. If you see a packet from this network, send it here. If you see a packet from this network, send it over there. You'll do that statically. And in a very small, simple networks with just a few networks, you can do it that way, static routing.
That's what we're going to do in the lab.
You're going to do some static routing. You won't do that in this lab. That's one of the early labs in the next class that you'll do static. But you'll find that with very big networks with a lot of changes and things, where your route can take along different methods, right? And packets can travel different parts, that static routing becomes impossible. It's just like doing static IP addressing for all of your PCs. We don't do that. We use DHCP, dynamic, right? So we want a dynamic protocol as well. So dynamic routing, the routers talk to one another and tell each other about their connected networks.
So it'll be like, like a business one, check email for the email server.
Remember, you're talking about this one network. This is between networks.
So why not use the email server? Is that on the same network?
Yeah, usually your email server is on the same network as you. However, in some cases, if you have remote offices, right? Like let's say you're here in Fremont, it's the main office, but you got an office in Newark, and you got another office in Union City, but your email server is here in Fremont, and they all use it, then they have to route to those. You'll have to have a router in each of those locations. A router in Newark, a router in Union City. You know, getting that information routed here when you want to use the email server. You know, that's better than having a separate email server in each one of those sites, right? But in order for that to work, the routers have to talk to one another and know how to send those requests. They do it with a routing protocol. Router C tells router B, I've got these networks. Router B then tells router A, let me tell you what router C told me. This, right? And so suddenly, they all know about each other because they've talked to one another. So there's a couple lab activities you're going to do next on Thursday. Those of you that are online will have separate packet tracer activities that are similar for you to do as well. Okay, so we're going to take a little break for about, come back at 8:30, and we're going to take a look at the next half of the presentation. So we're going to look at IP addressing in detail. Okay, so I know we've been getting out early here sometimes, but not tonight. So, but take a break. You need to do that. Those of you that are online, same thing. Take a little break for right now. Any questions from any of you guys online? It's pretty quiet there. You're still with me? Oh, Jenny, yeah, recordings, there's actually a document on the Blackboard site which tells you how to access the archives. But I'm not sure if I have that posted on the face-to-face class Blackboard, so I'll have to check that. Send me an email about that and I'll send you the document. It's really simple.
Yeah, I was able to find it.
You were able to find it? It is there. It's on the content. It's right by where the syllabus is located. Oh, looks like she heard you. This microphone's actually pretty powerful. All right, so let's take a little break. I'm going to just pause my recording here, which it's so weird. First, close that. Let's go back here, and then here I can see the recording button, but when I share an application, it does not work. So let me turn that off for a second. I'm here, and so let's just take a look at IP addressing, everybody, the ones that are still here. This is a critical topic. I'm going to get this down. We're going to get started tonight. So we're going to look specifically at addressing and how addressing is done, basically. So first of all, you got to know the difference between the physical address versus the logical address. So we're actually going to layer 2 and looking at the physical address. It's the address that's burned into the card, right? The network interface card from the factory. It has different names: MAC address, physical address, the hardware address, the Ethernet address, because that typically is the standard for the layer 2 address of the local area network. Can't be changed, so you can't reconfigure the MAC address unless you change the card, the hardware. And it's a flat scheme. It's not hierarchical. It's like Social Security numbers, right? Flat database. You can't look at somebody's Social Security number and say, oh, you're from California, right? Or, you know, you're from New York, right? They're a flat scheme. Everybody has one. There's no hierarchy to it. There's no way to organize Social Security numbers. However, you know, some people, you know, you're in California and when they started the system, you all got certain numbers in the early days that were all around the same. First 3 digits might be the same, but that's not the case any longer. So logical addresses are layer 3, also known as the protocol address. They're set by the administrator, so a person sets them up and assigns them. They're logical. They can be easily changed. You do it when you go out to the lab. You right mouse click, properties, you change the IP address to something different. And they're hierarchical. That means they have several parts, like phone numbers with area code prefix or zip codes, things like that, right? Different hierarchy. Now, layer 3, early ones, addresses come in different flavors depending upon the layer 3 protocol used. TCP/IP has IP, Novell had IPX, AppleTalk had AT address. They were all different in the way they were set up, but they all had the same features. They all had common attributes, including access to the upper layers. So TCP/IP, IPX, AppleTalk, they were all logical addresses. They all worked with the lower layers, the data link MAC addresses. They were all set by administrators. They all had a hierarchy on them as well. And each of those logical addresses had 2 parts. The length and the format of the protocol was different depending upon the protocol, but they all share the same formula, which was they have a network portion and they have a host number portion. So just like your phone numbers have an area code, right, a prefix, right, and then a certain part. So 659 is the Ohlone College. 656 is Mission San Jose, right? You would know some of the others. 657 is, I don't know, Centerville or someplace, or I don't know, somewhere else in Fremont, right? Different places. Okay. Now, IP is the de facto standard, so we're not really going to care about IPX or AppleTalk. When I first started with the Cisco program at the very beginning, this is now their 15th year starting up, we actually had to learn how to route IPX and AppleTalk also, because Cisco routers were connecting those types of networks too. You had to learn those protocols and set them up on the router. So some instances, CCNA study has gotten a little easier because now we don't worry about those other protocols. They're not even supported anymore because don't exist. Other things have gotten more complicated though. So IP addresses are the most common logical address. Everyone on the internet has one. They're a 32-bit number. That's IP version 4. 32 bits gives you 2 to the 32nd unique numbers. Remember, it's 4 bytes, each with 8 bits. There are over 4 billion possible different combinations. So you got 32 bits. They have all zeros, right? All the way to all ones, and different combinations in between. Each time you change a bit, you get a new number. So you have over 4 billion possible IP addresses. But maybe that's not enough. The population of the world right now is like 6 billion, right? So if everybody on Earth had an IP address, we wouldn't have enough. And there's more problems about this than just the fact that we wouldn't have enough for everyone to have one. So there is a next generation, IP version 6. The newest version of IP, version 6, or IPNG, uses 128 bits, yielding 2 to the 128th unique combinations. That's over that many possible addresses. I don't even know what that number is. Right? We got, billions, trillions. I don't know where you go from there. There's a lot. Actually, in this case, there's enough addresses for every person to have 65,000 addresses themselves, each. So, anyway, we'll never need more than that, right?
Is the problem going to be managing the IP addresses?
Well, there's some things that make it easier to do, yeah. So IP version 6 is slowly being integrated into the existing internet. As I said, China's using it already in great numbers. But IP version 4, 32 bits, continues to be the dominant form of IP addressing here for sure. And we're going to still use it. We're going to learn it in detail because that's going to help you most with the class and the certification. So IP addresses, we use a dotted notation to represent the value for each byte. So we convert the binary values of the IP address to decimal so that we can easily understand it and write it. Because we're into base 10. So 169 is actually those combinations of zeros and ones. 10101001. That's 169. 199 is that bit. 69 is that one, and so on. If we look at this, the way it works here, I bet I can't do that. I guess I can't do the little pointer anymore, huh? Does anybody know how to do the pointers where you can write on the slide for Office 2010? We got rid of that. Now, the way this value works is when you have a 1 here, that's the ones place, right? So you need to know the binary values. That's the ones place. This next value is the 2's spot, right? The next one over here is the 4's. Then this is the 8's, the 16th place, the 32nd place, the 64th place, and the 128th place. So this is 128, that's 1, plus not 64, plus 32, 128 plus 32 is 160, plus 8 is 168, plus 1 is 169. Okay, so that's how we get that value. 170 would be, you know, I lost my pointer too, a 1 here and a 0 there, because that'd be the 2 instead of the 1, 170. 199 is 1, the 2, and the 4, that's 7, plus the 64, plus the 128 is 199. 69 is the 64-bit, plus the 4-bit, that's 68, plus the 1-bit, 69. 137 is 128, plus 8, it's 136, plus 1, 137. Okay, so it's going to be important that you identify how to convert from binary, but for the purposes of the test, and really for the practical purposes of doing networking, you don't really need to do that either. There is a great little game, though, that's on the internet called the binary game. You actually have access to this in the curriculum. There's a link there, I believe. If not, I'll share with you the link later. But if you click this, it sends you to a website, which is probably not going to work over here. Nope. You won't be able to see it online, for those of you that are online. But anyway, I'll post this on the Blackboard site so you can get after this. This allows you to start this game sort of like Tetris, where things start to fall down, and you have to quickly convert to binary, or you lose the game if you don't do it quickly. All right, so there's a chance to go ahead and take a look at that. It's pretty fun. Binary game. Okay. Now, with dotted decimal notation, there are certain limits to the values that you can have in those 4 numbers. You have 8 bits, so if you have all 1s in there, it adds up to a certain amount. So with that in mind, which of these addresses are legal addresses? Third one is legal? Second one is legal, 12.1.2.2. What about this first one? No, because this 321, that's not possible, right? Because the biggest number you can have there is 255. Yeah, because you have 0. There's 256 possible combinations, but you start at 0, and you go all the way to 255. You might be thinking that 255, I've seen that a lot in the subnet mask, right? Well, that's because you have all 1s, right? That's 255. So this one's not good. The only ones that are any good are the second one and the last one, the 5th one, right? So those of you online, did you get those right? You didn't even try. Okay. Oh. Turned off my video somehow. All right, so the highest decimal number for any octet is 255, or all 1s in binary. So only these 2 values are actually legitimate addresses that could be used. So now, in early days, to get the best use out of the 32 bits that were available, IP version 6 used a class system. So they divided their networks up into different classes of networks. You're going to have to identify the class of networks. There are 5. Class A, B, C, D, and E. So they took those 4 billion addresses and they divided them up into different classes. Okay. The first 3 classes, A, B, and C, are usable for Internet hosts. Class D, a portion of that 4 billion, is for Internet multicasts. So we'll talk about that later, but a multicast is from 1 to many. So it's a different type of programming. So you're not going to have a multicast address on your home network to connect. You're going to have either Class A, B, or C. And then Class E were dedicated for experiments. So they kept some of those 44.9 billion addresses for, or 4.2 billion for experimental purposes. So computers on the internet can only be addressed using Class A, B, and C. Now, how do we know what the class is? Well, you know the class by looking at the first octet. If the first octet is between 0 and 127, that's class A. So here, our networks are, we're on the 10 network, right? This is what our student network is. That's class A. If the first octet is between 128, you notice we go from 0 to 127, then we start at 128 to 191 is class B. So if that first value, so out in our lab, we've been using 172, right, dot 16. So the 172, class B. Class C, the first octet is between 192 and 223. So 192, 168, 1 network, class C. Typically used home network, things like that. As we continue in the range, from 224 to 239, that's multicast, and from 240 to the end, 255, that's experimental, cannot be used. So, internet machines, hosts, can only be in these top 3 classes and ranges, from 0 to 223. So looking at that, what would be the class of this network? What is it? Class B, right? It's 180. You look at the first octet, it's in this range. That's class B. How about this one? D, yeah, 224 multicast would not be an internet. It would be on class C, or class B rather. How about this one? That's class C. It's 207. That's between 192 and 223. Actually, Aloni's network starts with 207. The Aloni public network. Class C. So the address class can be helpful to determine the network number and the host address. All right. So we can use the class to do that. With address classes, in a class A, the first octet, the first 10, the first 8 values are network values. And the remaining 24 bits are for hosts. With class B, the first 16 bits are network, and the last 16 bits are for hosts. And class C, the first 3 octets are network. Okay, so there's no arguing about that. It's class C. So 192, 168, 1.1. So 192, 168, 1 is network. Dot 1 is the host, where you could have dot 2, dot 3, dot 4, etc. So here's some examples of class A networks, 85.45.31.158. So the network here is 85, class A. For class B, it's 168.65, so the first 2 octets are network. That leaves you with these values for hosts, 16 different bits. And in class C, 210, 144, 235, that's network, and those are hosts. Okay, another little quiz here. Which part is the network? So remember, we got to figure out the class first. So this is class C. So 199.46.36. What about this one? Class A. So what's the network? 111 dot, and then this part, 121 is host. What about this one? A. So what's the network part? 7. What about this one? C. What's the network part? 222.8.56. That's the network. What about this one? Also class C. The network portion then is 192.168.16. That's the network portion. This one? Class B, right? From 128 all the way to 191 is B. 163.100 is network. So what's in red are the actual network portions. Remember, every address has a network portion and it has a host portion. right? So it's hierarchical. So we know that anything on that same network is going to share the network portion. And the host portion will have to be unique for every host. So just like your street address is the network, and every house on that street address has a unique street number, right, or house number for that street. I mean, you all live on fast lane, right, but you have different numbers. Maybe you don't all live on the fast lane. Maybe not. So the network addresses are written like this. So the network address for each one of those networks has zeros in the host portion of the network. So 199.46.36.0 is the network address for that network. The first usable address for a host would be 1. Yeah, you put a 1 in the host portion. That's an address you could give. Typically give that to the gateway. The gateway usually gets the first address. It's not always the case. It doesn't have to be. The computers don't care. But for our purposes, we usually assign that as the first address. So class A, the 11 is 11.000. Class A here is 7.00, and so on. Class B, the first two numbers, 00.
So what type of network are we getting from our ISP? To make DHCP and give us some IP address.
Well, they usually, you're going to get like a Class A from Comcast if you're on Comcast. Comcast is a big company. They have a whole bunch of addresses. So Class A is like 69 or something like that. But you only get one address within that whole range. A Class A network can give you 24 bits. And 24 bits is 16.7 million possible combinations. You know, this is all binary. Computers love that stuff. Like graphics, Super VGA graphics is 24-bit graphics. 24-bit graphics is how many colors? 16.7 million different colors, because that's how many bits you have with 24-bit color. Right? VGA is only 16-bit color. I think it's the Super VGA is I think maybe. I can't remember. But anyway, there's some that are only 256 colors, right? Some that are 65,000 colors, depending upon the number of bits. Okay, so in your addresses that you use to determine the network and the host addresses, there are a couple addresses that are reserved that you cannot assign to a host. The first one is the network address. Remember, that's the network portion, then followed by zeros in the host portion. So in this case, we've got 176.10 class B .0.0. So the 176 and 10 is network. The host portion, if they're all set to zeros, that's the network address, and it cannot be assigned to a host. In fact, most hosts will reject that if you try to type that address in, because the software will allow it to be assigned. The other address that's reserved is if you have all ones in the host portion. So all ones, all 8 ones is 255, right? So if you have an address that's 176.10.255.255, that's an address that's reserved for broadcasting. So networks need broadcasts. That means when they don't know who to send this packet to, they broadcast it. And they need a mechanism to do that. So there's a broadcast address that's used by devices when broadcast is necessary. Okay. So network numbers. How do you write a network number? The easiest way, starting out, is to first set the host portion to all zeros. So here's a network. What class is that? Class A, which means only the first 8 bits are network. So how do I write the network address? 84.0.0. That's the network address. Here's another one. This is class B, so that means the first 16 bits are network. How do you write the network number? .0.0 is the network address. Now, for this case, the first usable host would be 84.0.0.1. The next one would be .2. The next one would be .3, all the way to 255. Then this one would be 1.0, and 1.1, and 1.2, and 1. We have a lot of possible combinations with that. We actually have 24 bits for hosts. We've got over 16.7 million possible host addresses for that network. Say the broadcast numbers. So how do you write a broadcast number? You set the host portion all to ones. Here's the same address. What's the broadcast? This is class A. 84.255.255.255 is the broadcast. This one? Class B. That's 398. 255 is the broadcast. Great. Okay, because the network number provides logical order, you can't just randomly assign addresses. One organization administers IP addressing. That's IANA. We talked about them before. The Internet Assigned Numbers Authority. These addresses are assigned to companies. Early days, it was governments and big corporations that got the bulk of the numbers, right? Aloni itself, we got 4 Class C networks, all given to us, because they were given us in early days when they had lots of addresses. They figure, oh, community college, learning institute, someday they might have 1,000 computers. So they gave us 1,000 IP addresses. That's how many we got, but we quickly outuse that. We have easily over 1,000 computers on this campus alone. We probably have closer to 5,000 computers. And so we got a few issues with IP addresses. But anyway, addresses are controlled by IANA, and they assign that through ICANN. Controls IANA, the Internet Corporation for Assigned Names and Numbers. So Class A addresses, again, the first octet is between 0 and 127. You've got 24 bits for host values, right? That means you've got over 16.7 million possible addresses that you can use in a Class A, right? There are 126 Class A addresses, because we go all the way from 0 to 127, which is actually 128, but you cannot use a network starting with 0, and you cannot use a network starting with 127. Now 127 you should have seen somewhere before. 127.0.0.1, what is that? The loopback address. So in the early days of TCP/IP, they took a whole Class A network with 16.7 million possible combinations and gave it to the loopback. That's why you have that little exercise where you could do, you could do a ping to 127.0.0.1, it worked, and you could do ping to 127.0.0.2, and that worked, and ping to 127.255.255.254, that worked. But when you tried to ping 127.0.0.0, what happened? In the lab, it didn't work because that's a network number. And when you try to ping 127.255.255.255, that didn't work either because that's broadcast for the whole network. Anyway, only large organizations such as the military, governments, agencies, universities, and large corporations have Class A addresses. Cable modem ISPs in early days like At Home and what became Comcast eventually were 24. PAC-Bell DSL users had 63 addresses to give to everyone. Now, for your home network, you have to have a public address that's on the internet. You have to have an internet value that you could have people connect to you through the internet, and they do, through your IP address that you got from your ISP. So Class A addresses account for 2 billion of the possible IP version 4 addresses. That's 50% of all the addresses. Remember the 4 billion addresses possible out of 32 bits? half of them are Class A. Class B addresses use the first 2 octets per network. And the first octet has to be a number between 128 and 191. So the 172 fits in that category and so on. Remember, 127 was Class A. The next one, 128, is the beginning of Class B. And it leaves you with 16 bits for hosts. Well, with 16 bits of hosts, you still have 2 to the 16 possible addresses. That's 65,536 nodes that you can have. There are 16,384 Class B networks. So remember, you can go that previous slide, right? 192, right, can be the first one, right? And then 192, second number can be 1, so 192.1, 192.2, 192.3, 192.4, right? So you've got a lot of possible combinations of Class B network addresses. Whoops. Class B represents another 25%. So half of the address space for Class A addresses, another quarter is Class B. So 3/4 of all the addresses are already used up between Class A and Class B. Class B addresses are usually assigned to organizations, including corporations such as Cisco, government agencies, big school districts, things like that. We've got Class B networks, addresses. Class C, the first 3 octets are network. The first number is between 192 and 223. You have only 8 bits for hosts. With 8 bits for hosts, that's 2 to the 8 possible addresses. That's 256 nodes that you can address with a Class C network address. That's
So if you move up, you have to get a hold of the IP address to make your own network.
yeah, and that doesn't really work. So this is early days of the networking, how they divide things up, and they become its legacy approach, but we still need to use the same addressing with its legacy attributes, like the classes. Classical networks, Class A, Class B, Class C. There are certain routing protocols that you'll learn about, the old ones that were first established, that use classes, and still are classful routing protocols and do things by class. So it becomes an issue still. All right, so Class C, smaller network, right, 256 nodes. There are actually over 2 million possible different Class C networks, right? So 192.1.0, 192.1.1, 192.1.2, and so on and so forth. 2 million possible Class C networks. Class C networks represent 2.5% of the total IP version 4 address space. And, whoops, what did I do wrong there? Oh, don't look. We're almost done here. Now, most home networks use Class C, right? So my home network is 192.168, right? And everybody else's uses a similar one. We use Class C at home because we're never going to need more than 200 addresses at home, right? You might have 4 or 5 computers in your home network, never over 200. But still, with everybody having their own home network nowadays, we've got a lot of address need. And this was recognized in early days, so the people who are in charge of the standards decided that they would take certain addresses and reserve them as private addresses. So there's public and private IP addresses. So no 2 machines that connect to the public network can have the same IP address because public IP addresses are global and standardized. However, private networks that are not connected to the internet may use any host address as long as each host within the private network is unique. So a certain request for comments, RFC 918 set aside. 3 blocks of IP addresses for private internal use. Connecting a network using private addresses to the internet requires that you have a device that does network address translation, or NAT, that translates your private IP address to a public address. So that's what we have here at Ohlone. If you look at our addressing, let's see if I can, this works. I don't know. For those of you that are online, you'll just need to go through your command prompt, although you're not going to see Ohlone's address. Let me just try something here. See if this works. Alright, so I got the command prompt up there. Yeah, actually that works. Okay, so, wow. IP config, right? Still all right. Oh. A lot of different connections here on my laptop. Well, I've got 2. I've got the wireless, so I didn't turn off my wireless interface on my laptop here, so I've got Renegade connected, which is the first address space was listed up there, so that's the 172.30.2.247. So the 172 is what kind of network? A, B, C? Class B. And then the second one is my actual interface card. You can see both of those have physical addresses listed there as well. Actually, it has IP version 6 addresses listed there, which we're not going to really deal with much right now, but Windows 7 already has that in place, right, to use. But my IP address, version 4 address for my wired connection is 10.2.201.90, so it's a Class A. So our network here uses Class A network 10, which happens to be one of those private IP addresses that we talked about in that previous slide. Same thing with the Renegade, is 172.30 is a private IP address. So here internally on this network we use private addresses, but when we get out to the internet we have to go through a public address. So let me do something here. First of all, let me shut down my my wireless. Okay, so now I just have the one connection, my wired connection. And when I do that trace route again to google.com, so it got the address from Google through DNS. It's 174.125.224.100. So Google actually has Class A network, right? Big companies, they've got the money and the resources and the need. And then as I make my way through the network, I go through different hops there, right? Now I start at 10.2.1.1. That's my, what is that? 10.2.1.1. Is that my IP address, or is that my, that's my gateway. As you see up here in my configuration, that's my gateway. So it goes there because Google 74 network is not part of my network, so it has to go to the gateway. And then it goes to 192.168.210.2. That's another device, another router, another hop. It also is a private IP address. And then it gets to 207.62.190.10. That's Ohlone's public address. So each one of you, as you're going out to the internet, you have to go exactly that way. And when you leave Ohlone, all those requests look like they're coming from one place, the 207.62.190 network. All those requests. And when you leave here and go out to go do something out there, no one knows where that request came from except it comes from Ohlone. That's why people can be here and do all kinds of things in the network. And there's no trace. There's no way for anyone out there to know who's doing something here. Like on my home network. Occasionally, I have teenage kids, right? And occasionally I get an email from Comcast telling me that someone in my network has been downloading, proprietary movies and music, and it needs to stop. They can't tell me who, and when I ask my kids, they deny it. But somebody, there's no way for them to tell. As far as all they know at Comcast is from my network, from my public address at home, somebody's going to sites and downloading music illegally. Okay. All right, so let me, as we go along the way, you'll see that all these addresses are, again, IP public addresses. I'd have to stretch this out a little bit here. Can't do that, though.
So in the admit, how do you know which one is public, which one is...
Okay, let me go back to where I was before. Okay, so how do you know which is public, which is private? Because some time ago they decided these would be the private ones. So notice 10 is private. So Ohlone uses 10 because it's Class A. And 10, remember, Ohlone Class C, we got 4 Class C networks. We had 1,000 addresses. We've got 4,000 computers here. So we use Class A, 10, because that gives us 16.7 million possible host computer addresses, more than we'll ever need. Class B is 172, so the Renegade Wireless, we put that on 172.30, which is Class B, private network. And then Class C, we don't use that here much, but that the one on the firewall, we use the Class C network there. But now the 207, that's public, right? That's not on this list. So that needs to be configured on the outside. That's our public look. So when you're at home and you go to the Ohlone webpage, you go to 207 number. That's how you get to our webpage, not to a private number. Now we use 10. Chabot uses 10. Mission College uses 10. Foothill College uses 10. De Anza, they use something else because they're unique. No, they all use 10. Every private network uses 10 in their private network behind their firewall. But when they leave the internet, they have to have a unique number. Okay. Oh.
So they're not really running out of IP addresses.
That's right. Ohlone has 4 Class Cs, 1,000 networks. We only need 1. Well, we need more than 1 because we have other devices. We have email, we have web, we have a backup web server, we have a DNS server. Each one of those are out there and has to have a public address. So we use a handful of addresses that are public. Okay, so in the early days of the internet, IP addresses were allocated to organizations based on requests. Somebody asked for one, they got them. We had so many, we had 4 billion. Sure, you can have, here, take 1,000. All right. And there's no medium size. Class A, the networks are 16 million. Class B is 65,000. Class C is kind of small, only 256. For organizations, 256 was too small. 65,000 way too many. So one thing that they did is they created the subnet mask. That's that other part of the address that sort of divides what's the network part and what's the host part, to help break single-class networks into smaller little pieces. So, your ISP gives you 1 address, but if you have a small business and you want to do business DSL, they'll give you a block of 8 addresses, which you can then have a web server, an email server, and that's all you need to set up. And then your network behind it can be private addresses. So you get to have several devices on your public network. You pay more for business DSL, multiple addresses. If you want, at Comcast, we did this for a while. My wife was working. She had to have a separate IP address for her device. We actually had 2 addresses from Comcast. We paid an extra $5 a month for that extra address each month. Now they don't need that with VPN and things like that. We just use one address.
Do we purchase our own IP address?
Well, you kind of do that when you subscribe, right, to your ISP. They give you, you're entitled to one. They control what that one is, though. You can't then sell it to someone else, right? You just sort of get that address assigned to you. So no, I don't think you can actually go down and buy anymore. They might all be accounted for. Okay, so that's just the first look at addressing. We're going to do more with that next week, quite a bit more. And you've got some activities. Those of you that are online need to do the packet tracer activities that are embedded in Chapter 5. There's 2 of them. You'll have to turn those in on Blackboard. And then for those of you that are here with me, and those of you that should be here that are online but plan on being here Thursday, there's 2 labs, and I'll have copies of those for you guys to work on too, for Chapter 5. All right. So I've got this little video. I don't know if you want to cap it off the evening to kind of review Chapter 5. We haven't looked at that in a while, so I want to play that. I can't really play the videos over this web application, so I'm going to let those of you that are logged on go for the evening. You can check that video out online. It's available on the Blackboard site. So you guys have any questions about the assignments? Looks like next week we might have 2, we'll have 1 session remotely, and the other one's going to be just paper and pencil. You guys are going to have to do those activities on your own. Okay. Any questions from those of you online? All right. Guess you're still there. You're watching the Giants game or something. I don't know. There you are. Huh? Questions out there? That's next week. Topic for the next chapter.
Did we jump ahead with the IP addressing? Is that Chapter 6?
Chapter 6 is, yeah, you jumped ahead a little bit. Chapter 6 is a pretty heavy topic. So we want to get started with that. So you got some basis of IP addressing kind of down now, and then we'll look at how they devise some techniques to solve the problem of this class system and the way they set up the networking as well. Okay, see you guys Thursday that are coming in, and I'm going to shut down, turn off the recording now. I'll do that over here.